Hello, Chemistry 30. This is our first lesson in the chemical equilibrium unit. This is Introduction to Equilibrium. In this lesson, we will review Chemistry 20 concepts that are important for the chemical equilibrium unit. We will review the collision reaction theory, then move forward with equilibrium, types, describing, and percent chemical equilibrium. First up, Chemistry 20 review. How many moles are in 3.45 grams of silver chloride? And how many moles are present in 500 milliliters of solution of 0.75 moles per liter sodium hydroxide? Pause the video and attempt this example. In our first question, we are given grams of silver chloride. Therefore, we have to use the molar mass of silver chloride to convert grams to moles. We always start our calculation with the value that is given, and we want our answer in moles, so 1 mole goes on the numerator, and 143.32 grams goes on the denominator. Grams cancels out, and our answer is left in moles, 0.0241 moles. 3 significant digits because that was the lowest going into the calculation. In our next example, we are going to start with the single unit, 500 milliliters. We then have to convert the milliliters to liters, dividing by 1,000. Once we are in liters, we can then times our value by 0.75 moles on the numerator and divide by 1 liter on the denominator. This cancels out liters, and as a result, our answer is left in moles, 0.38 moles, 2 significant digits because that was the lowest going into the calculation. In our next example, we are given a chemical equation. How many moles of F2 are produced if 32.44 moles of Kf are decomposed? Pause the video and attempt this example. We have to convert moles of one substance to moles of another. Therefore, we must use the molar ratio in the chemical equation. We must use stoichiometry. Always start your calculation with the value which is given in the question. 32.44 moles of Kf. We want our answer in moles of F2. Therefore, on the numerator, we have 1 mole of F2. The 1 comes from the coefficient in front of F2 in the chemical equation. We need to cancel out moles of Kf solid, so 2 moles of Kf solid is on the denominator. The 2 comes from the coefficient in front of Kf solid in the chemical equation. As a result, our answer is left in moles of F2 gas. Our answer is 16.22 moles. 4 significant digits because that was the value which we started our calculation with. And finally, our last example. In an experiment, a student calculated the mass of product to be 100 grams, but only measured 93.5 grams of product. Calculate the percent yield and percent error. Is this experiment valid? Pause the video and attempt this example. Percent yield is the actual yield divided by the theoretical yield times 100%. The actual yield is the amount that is measured. It is always given in the question, 39.5 grams. And the theoretical yield is the value that is calculated. It is the value that you should get if there was no percent error. So we are going to take 93.5 grams, divide it by 100 grams, and times that value by 100%. This means that in our chemical reaction, we yielded 93.5% of the product. And finally, our percent air, which is equal to the actual yield minus the theoretical yield divided by the theoretical yield and times by 100%. And this would give us a value of 6.50%. Since this value is under 10%, we can say that this experiment is valid. It's also important to note that these lines on either side of our equation, these represent that this is an absolute value, meaning regardless of its positive or negative value, we always represent it as a positive value. And that brings us to the collision reaction theory. Remember, a reaction occurs when we have effective collisions between reactants. Well, if reactants can collide to form products, that means that products can also collide to form back into reactants. Equilibrium facts. Equilibrium occurs in a closed system when there are no observable changes. That means the macroscopic properties remain constant. These are large-scale properties that we can observe and measure. For example, concentration, pH, and temperature. At equilibrium, these properties will never change. Dynamic equilibrium is a balance between two opposite processes occurring at the same rate. That would mean the same rate of reaction. If we look at our chemical equation, we have a forward reaction where reactants are turning into products. We also can have a reverse reaction where products can turn back into reactants. Both of these processes are happening at the same time when they're at equilibrium, and both reaction rates will be equal. Remember, reaction rate is the speed at which a chemical reaction proceeds and is typically measured in moles per liter times seconds. Therefore, our equation is rate of reaction is equal to the amount of reactants being used divided by the time. And again, the 5 factors that affect reaction rate are temperature, surface area of the species, concentration of the species, nature of the reactants, and the addition of a catalyst. And that brings us to establishing equilibrium. First, let's determine what this graph is showing us. We can see on our y-axis we have concentration, and on the x-axis we have time. Therefore, this graph is representing reaction rates. In blue, we have the reactants. This is telling us the rate of the forward reaction. In red, we have the products. This red line would be telling us the rate of the reverse reaction. We can see at time 0, we have a high concentration of reactants. Therefore, we're only starting with reactants, and we are starting with 0 products. At point number 1, the forward and reverse reactions will proceed at different rates. Well, this will depend on the concentration. It's important to know that every time a line goes downwards, that means we are decreasing the rate of reaction. And when a line goes upwards, we are increasing a rate of reaction. Since we are starting with only reactants, it will have a high concentration. But as this reaction proceeds, we will start to produce products. That means we have less reactants, and therefore the forward reaction rate will start to decrease. If we look at our products, originally we have no products, but as the forward reaction proceeds, we start to produce products. Once we have products, we can have collisions, and therefore our reverse reaction will start to increase. And this has been explained in point 2. With only reactions, the forward reaction rate will be faster, as it is the only possible reaction. At point 3, as products are formed, the forward reaction will slow, and we can see that this line starts to decrease. And the reverse reaction will then speed up, and we can see that the products will start to increase. Their rate of reaction is increasing. Finally, at point 4, the forward and reverse reaction rates will become equal. When they become equal and they flatline, we are now at equilibrium. That brings us to types of equilibrium. The first is phase equilibrium, which involves a single chemical substance existing in more than one phase. A good example is water in a sealed jar. Remember that it has to be in a closed system. What we are seeing in this picture is that we have liquid water, which will evaporate. When 1 mole of water converts from liquid to a gas, other particles of the gas will then condense back into a liquid. So we are seeing a continuous process of liquid water being converted to gas, and at the same time, the gas water is then being converted back into a liquid. That is 2 separate processes that are occurring at the same time. The next type is solubility equilibrium, which involves a single chemical solute interacting with a solvent at saturation. So in our picture, we can see that we have put a cube of NaCl in water. And what happens is, since water is polar, it will be attracted to the ions and it will separate those ions, dissociating NaCl in water. We need excess NaCl in water to create a solubility equilibrium. That is because we need both processes happening at the same time. We have seen the first process. NaCl solid is being dissociated into water, which is going to form its ions Na plus and Cl minus. Once we have saturated the water with ions, we can no longer put any more ions in the water. So as we proceed to dissociate excess NaCl and form new ions, we have to then remove ions from the water. So we will then see ions in the water, Na plus and Cl minus, recrystallize back into NaCl solid. Again, we need excess solute in water to establish a solubility equilibrium. And our last type is a chemical reaction equilibrium. This will be our major focus in Chemistry 30. It involves several substances, reactants, and products in a chemical reaction. Here we can see a chemical equation where, again, we have a forward reaction in which reactants are being turned into products, and we also have a reverse reaction where products are being turned back into reactants. Both of these processes will happen at the exact same time. Describing equilibrium. There are 2 ways to describe equilibrium. Our first is our major focus, equilibrium constants, which is represented by K. It represents all substances in an equilibrium for the same reaction. More will be learned about equilibrium constant in future lessons. The other way to describe equilibrium is percent reaction or percent yield, but this only represents a value for one of the substances in the reaction. Percent reaction is the yield of product measured at equilibrium compared to the maximum possible yield of product, which we could calculate using stoichiometry. For example, we can think of this as percent yield, where our equilibrium value would be our actual value, and our maximum possible value would be the theoretical, which we could calculate using stoichiometry. This can be expressed and used in terms of equilibrium, and we can get a percent yield. That would tell us that at equilibrium, we only have 78.0% of the products from our maximum possible amount. We will not use percent reaction or percent yield very much in this unit. Percent chemical equilibrium. This describes how much reactants and products will be formed and whether the reaction is at equilibrium or is not. First, we have a non-spontaneous reaction, and this is where there is no evidence of a reaction at all, meaning that we will essentially form no products. This will not be in equilibrium. Our next type of reaction is a reactant-favored equilibrium, and that is when there are more reactants than products at equilibrium. We are saying that the products will be less than 50% at equilibrium. Our next is a product-favored equilibrium, and this is when there are more products than reactants at equilibrium. And this represents that we have greater than 50% of our products. And finally, we have a quantitative reaction. This was learned in Chemistry 20, and this is when there is no equilibrium and the products can be determined using stoichiometry. This means that our reaction essentially proceeds to completion, and we can say that our products will be greater than 99%. All of our reactants have formed into products. And at times these numbers can be confusing, but they always represent the products. So in a non-spontaneous reaction, our products are less than 1%, meaning a reaction has not occurred. In a reactant-favored equilibrium, our products are less than 50%. In a product-favored equilibrium, our products are greater than 50%. And finally, in a quantitative reaction, our products are greater than 99%, meaning our reaction has essentially gone to completion. Moving forward, we will explore Le Chatelier's principle.